We are going to wrap up our study of probability this week by looking at tree diagrams and Bayes' rule. So sometimes it's helpful to create a visual representation of if we have multiple events occurring. So before we talk about what's highlighted in yellow, remember we're talking about multiple events occurring, which means we're going to be multiplying probabilities, just like we did all of the time that we've been working so far. We're going to multiply the probabilities. Now, a tree diagram comes in handy when we have two or more events, and remember the two or more events is what tells us that we are going to have to multiply probabilities. And these are with conditional probabilities, which means the probability of one event is changed based on the event that occurred before that. So for example, at a local college, a survey of students who choose to live on campus revealed 10% are seniors, 20 juniors, and the rest underclassmen. The most desirable dorm is the Gold Dorm, and 60% of seniors live there, with 15% of juniors and 5% of underclassmen. So these are conditional. So the 60% means that's the probability that a student, given they're a senior, lives in the Gold Dorm. Okay? So these events are conditional and different. So let's take a look at that example and how we might look at a tree diagram to help us. So I've already written it out for you so you don't have to spend time copying it down. But I'm starting here with college students. And notice I'm not putting the number of college students because I don't know. I just know that that represents 100%. Then I'm saying, and I'm just going to choose whatever they give me first as the first condition. So each of these sections is essentially an event or a condition. And the first event or condition in this case is the class. So senior, junior, underclassmen. So notice what I've done is I've broken it off, senior, junior, underclassmen, and I've written those values. And what I want you to notice is that all adds to 1. And that's important because we talked before about how our sample space must add to 1. From here, this is where the tree diagram is so helpful to us, because if it wasn't conditional probabilities, if it wasn't based on whatever the condition they had before, then it would be a lot easier to figure out. Just multiply, 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 no big deal. But here, seniors have 60% in the Gold Dorm and 40% not in the Gold Dorm. And again, this adds to 1. And juniors have 15% in the Gold and 85% other. And again, this adds to 1. And of course, underclassmen, 5%, 0.05, and then 0.95 or 95%, again, adds to 1. So each time I branch out from a part, it always has to add to 1. Now, the big idea with tree diagrams is this column right here. This is the whole purpose of making a tree diagram. So first, let's talk about how to find those values. To find this value, I'm taking 0.1 times 0.16, and that gives me 0.6. Remember, I'm multiplying because these are multiple events occurring. This one is 0.1 times 0.4 gives me 0.4. So all I'm doing is multiplying along the branches. 0.2 times 0.15 is 0.3. 0.2 times 0.85 is 0.17. 0.7 times 0.05 is 0.035. 0.7 times 0.95 is 0.665. So that's great. If they said, out of all of the students, what's the probability that it's a senior in the Gold Dorm, I could answer very easily because I've already figured it out. A senior in the Gold Dorm is 0.06. That's the probability. Where things get a little bit trickier is when I look at a question based on what I've just found out, like this, that says, what is the probability that a randomly selected resident of the gold dorm, so again, this is going to be conditional because we're telling me that it's a resident of the gold dorm. So it's probability of something given gold. And what's the something? That person is a senior. So that's the question. So what's the probability that's a senior given it's the gold dorm that I've chosen a senior? So just as we have been doing, the numerator is going to be someone who's in both categories, senior and gold. And look, that's the one we've already looked at, which is 0.060. The denominator, however, is anybody in the gold dorm. So keep in mind that these are people in the gold dorm who happen to be seniors. These are people in the gold dorm who happen to be juniors. And these are people in the gold dorm who happen to be underclassmen, which means my denominator is 0.06 plus 0.03 plus 0.035. So now I can continue to find my probability of senior given gold, which is 0.06 divided by 0.125, which turns out to be 0.48. And so the probability that a randomly selected gold dormer is a senior is 48%. So I would write this out. So notice here I'm giving it as a decimal, and then I'm going to write the probability that a randomly selected resident of the gold dorm is a senior is 48%. So when I write it in my sentence, I write it as a percent. When I write it in my work, I write it as a decimal. So it's often easy when the teacher goes through a tree diagram to follow along with the logic, but when you actually make a tree diagram yourself, it's more difficult. So if you would, I'd like you to try to create a tree diagram first, and then we're going to talk a little bit more about it. But if you would, I know I didn't put it in blue or anything at the top, but if you would, just press pause. See if you're able to create a tree diagram, keeping in mind that I want, don't stop short, make sure that you multiply the probabilities to find the answers at the end. So once you've done so, then press play to see how you did. So the way that I set mine up is I again started by looking at the first category, which is drinkers. So binge drinkers, moderate drinkers, and abstainers. And notice that I took my college students, I broke them into 3 groups. The other thing that I'm looking at, the other variable that I'm looking at, is whether or not they've been involved in an accident-related injury or have an accident-related injury. So again, notice that these are changing. So this is 17% of binge drinkers, which is different than the amount from other categories. So 17% binge, 9% moderate, 0% non-drinkers. So that's my second branch, I guess, which is injury or not, injury or not, injury or not. Again, keeping in mind that if they tell me 17% are injured, that means 83% are not, 9% are, which means 91% are not, 0% are, which means 100% are not. You get the idea. And then the most important part is, of course, to find these values, which are found by multiplying. Again, this would be 0.44 times 0.17, etc. So I'm not going to go through all of those again, but this is hopefully the tree diagram you came up with. So now that I've made my tree diagram, which you can see I have copied again up into the upper right corner, I want to answer some questions. What's the probability that a student did not have an accident? So again, if I'm looking at that they didn't have an accident, I'm looking at no accident here. I'm looking at no accident here. I'm looking at no accident here. So that probability would be that I have to add up all of the people who didn't have an accident, and I find 0.8928. So now I'm asking, assuming that they didn't have an accident, what's the probability that that person was a binge drinker? So again, this is a conditional probability, which means the numerator should be that they're a binge drinker with no accident, and the denominator should be everybody who didn't have an accident. So as you can see, this 0.8928 that I figured out is going to be my denominator. The numerator is just the people who were in the binge category, which is the 0.3652. Bayes' rule, which is another way essentially for us to figure out a conditional probability, can help us to do this without a tree diagram. So what I can do, and again, I wouldn't do it if I've already made the tree diagram because it's just extra work, but what I can do is I can say, okay, the probability of B given A times the probability of A as my numerator, and my denominator is the probability of B. So here basically I'm saying the probability of B given A, so no accident given binge, would be 0.83, times the probability that they're a binge drinker, which was the 0.44. And then the no accident, notice what I'm doing here is I'm essentially doing the same calculations that I did up here to find the no accident people. So again, could I do it without a tree diagram? Yes, I could. I personally find tree diagrams helpful in order to be able to answer questions like this because I'm a visual person and I like to see it written out. But nonetheless, Bayes' rule can help us to determine the outcome. Let's look at one more question together before you try one of these completely on your own. So here we have 77% of accidents, the driver was wearing a seatbelt. 92% of those drivers, there was no serious injury, while 63% of belted drivers escaped serious injury. So we're going to make a tree diagram and then answer some questions. So we'll get to that question in a minute. Let's just look at the tree diagram. So what I'm looking at is people who had accidents. So when I start, I've got accident. Then I'm saying, okay, well, they either wore a seatbelt or they didn't wear a seatbelt. And 77% of people in accidents, the driver was wearing a seatbelt, which means 1 minus that, or 0.23, is no seatbelt. From there, we're talking about whether or not they had a serious injury. 92% of those drivers were no serious injury. Those were the people who were wearing the belt. So notice no serious injury, 0.92. The complement of that, 1 minus 0.92 or 0.08, those people did have serious injury. And then for non-belted drivers, 63% of drivers escaped serious injury, so 63% did not have serious injury. 1 minus 0.63, which is 0.37, did. Just as before, I then do my multiplication to find my solutions, and these are the numbers that are going to help me answer the question. So now it's time to look at the question. The question says, find the probability that a driver who was seriously injured, so this is the given, wasn't wearing a seatbelt. So I am finding the probability of no seatbelt, because it says wasn't wearing a seatbelt. So the probability of no seatbelt, assuming was injured. So my numerator here is the people who are in both categories, no seatbelt and was injured. So looking at my 4 values here, I've got no seatbelt and serious injury was 0.0851. That should be my numerator. My denominator is anybody who was injured. So these are the people who were injured with no seatbelt, but some of my seatbelt people also had a serious injury. So on my denominator, I'm actually going to add 0.0616 and my 0.0851. So that's going to give me 0.0851 over 0.1467, and that gives me 0.5842. And again, that's my decimal answer, which is the correct decimal answer. But I'm going to go ahead and write a sentence that explains it. I said, even though 23% don't wear seatbelts, they account for 58%, 58.42% of all serious injuries. So what have we learned? Wear your seatbelt. One last one for you to try on your own. This one's a great practice for you. So again, press pause, read through the question, make the tree diagram, answer the question that I've asked, and then press play to check your work. So here we have ovarian cancer affects 1 out of every 5,000 women. So again, this one's a little bit different. It gave me 1 out of 5,000, which means I'm going to turn that into a decimal by dividing, which means 0.0002. Is that too many zeros? Should it be 3 zeros? Yeah, 0.0002. A new test is able to correctly detect ovarian cancer in 99.7% of women who have the disease. So those who have the disease, it's pretty accurate. However, it gives false positives to 5%. So false positives to 5% of the women who do not have ovarian cancer. So first thing I'm going to do is make a tree diagram, which should look something like this. So again, cancer is 1 out of 5,000. Not cancer is everybody else. That's where I got those two values. And then I said 99.7% of women who have the disease will get a positive test because it's that accurate. So a positive test for a person who has cancer is the correct diagnosis. And notice I've gone out to several decimal places on all of my values here. And the reason that I did that is because I'm dealing with very small values here at the beginning. So you don't want to round off too much or your final answer is going to be inaccurate. Again, the negatives would be everybody who didn't get a positive. The other one says it gives a false positive to 5% of women. So again, the 5% goes here, 95 here, false positive. And then I've multiplied to find my solutions. From here, what I'm looking for is essentially, I'm looking for the probability that a woman who tests positive actually has cancer. So this is probability of cancer given positive. That is what I'm going for here. So cancer given positive means my numerator is people who are positive and have cancer. My denominator is everybody who's positive. So my numerator is positive who have cancer, which is 0.0001994. The denominator is everyone who tests positive, which is both the people positive with cancer and the people positive without cancer. Notice that I've added them together, and this is my final probability. So then the question says, comment on whether you feel this is a good alternative or a good method. So we know that basically 0.0, well, let's look at it as a percent instead. 0.397% of people who have cancer or who test positive actually have cancer. So is this a good method? I don't know. It seems to be that If less than 1% of people who test positive don't have cancer, that's a whole lot of women who are very scared for no reason. So is it a good method? I don't know, because we might have to look at what are the alternatives. So if this is just a first step, yeah, maybe this is a really good thing to do, and then the next step would be to do a biopsy, etc., etc., etc. So again, use a little bit of common sense here, but this number is astoundingly low. It means that assuming someone tested positive, only 0.397, so less than 1%, actually have cancer.